Okay, this is a quick video to go over the quiz. Questions form A and B. You can certainly scroll through to whatever questions you're interested in, but I'm going to try to work you through and give you some clues for the test as well, so you want to make sure, you might want to make sure and watch the whole thing. Okay, so let's get started. So on form A, we had this question, and it said a negatively charged rod is brought near a neutral metal sphere, and which is held on an insulating stand. And recall, the insulating stand is to make sure there's no charge transfer to anything else without us being very intentional about it. And it says if we hold the rod near the sphere, well, that's induction. This is induction. This creating a charge distribution without touching, this is induction. And then have someone touch the sphere. Now, some of you may have thought this is conduction, but it's not. It's grounding. And we talked about this in class, this idea that if we transfer charge off onto the earth, then it's grounding because the surface of the earth is larger. And that's exactly what's happening here. I gave the example in class of charging the water faucet and then touching it and the charge transferring to me and then off onto the earth because it's a larger surface. Also, the induction, conduction, and a charge value is not even a choice. So if you were confused, if you'll remember in class when we gave conduction, we started with two metal spheres actually already in contact. And I'm going to draw that on the bottom down here. And then we brought the charged rod in. This was induction, conduction, and grounding. I'm sorry, induction and conduction. The example for the quiz was induction and grounding. So let's talk about the charge. So the negative rod comes near. That means the electrons in the metal sphere are repelled, and they're going to move a little bit further away, leaving a positive charge on the surface closest to the negative rod. And when we ground it, that side that we're grounding looks like there's an excess of electrons, so those electrons are going to move off onto the earth. So if electrons are removed, then indeed we have a positively charged sphere when we are done. All right, form B just had the opposite. You still had this charged, neutral sphere, and this time we had a positively charged rod. Well, a positively charged rod is going to attract the electrons, leaving a net positive side on the other side of the sphere. And when we ground it, then the electrons are going to come in. This side looks like there's a shortage of electrons are going to come in, and then we're going to be left with a negatively charged sphere. And a good strategy for the test is actually just drawing it and working through it step by step. That way you don't make a mistake. All right, each of two identical charged objects carry a net charge. The objects are made from conducting materials. That allows you to know that the charge is going to transfer readily between them when they're touched later. One of them is attracted to a positively charged glass rod, which would mean that it has an original negative because opposites attract, and the other is repelled by the rod, so it must be the same charge, positive. After the objects are touched together, it's found that they each repel the rod. That means they both need to be negative. So what this means actually is that initially we had a shortage of electrons in one and an excess of electrons in another, but since they both end up positive at the end of the transfer, there wasn't enough electrons to go to both and make them neutral and then get an excess. There was a net shortage. Think of it like there were 3 electrons extra on one and the other one needed 8 electrons. Well, clearly there's not enough electrons to transfer and give us a net excess. Okay. All right, and then form B had just a slightly different scenario. It said a negatively charged rod. So you had a negatively charged rod, and one was attracted, so that means that it was positive, and one repelled, that means it was negative. and after the objects are touched together, they're both found to repel, so they're both negative. Well, in this case, there is a net excess of negative charges, so that both are negative at the end. Okay, in a closed physics classroom, Tracy conducts an experiment to see how charge is transferred. She rubs a balloon on a piece of fur that's charging by friction, then attracts it to the wall. As she approaches the wall, remember that's going to be charging by induction, and then there's this localized net positive on the surface of the wall that'll allow it to cling for a little bit. Please note that the wall is polarized. We haven't really talked about that a lot in class. The rest of this came up in your homework and your online exploration of this stuff, but the wall is an insulator, and insulators don't have a sea of free electrons, and so the electrons are not going to move readily, and we did talk about that, but what actually happens with them is that the electron cloud becomes a little bit mushed, for lack of a better term, and so that it sort of moves out of the way. But the electrons don't physically move off the atoms like they do in conductors, and this is called polarization. So it says sometime later the balloon falls to the floor. Well, the reason it's falling to the floor, we talked about this in class, is that water is a polar molecule, and it's actually attracted to the charges on the balloon, and it'll actually take off any excess charge or donate electrons if need be, to kind of balance out that charge over time. The more vapor there is in the air, the more water vapor, the faster this process happens. The less water vapor, the slower this happens. And truly, this is why you get shocked on a doorknob more frequently in the wintertime when it's drier than when it's humid out, because there's so many water molecules taking that excess charge or resolving that excess charge issue during the summertime. You don't have as large of a problem with static electricity. Okay, or static discharge, better. The key here is that you picked up on the fact that this is a closed physics classroom. So in a closed classroom or closed, isolated environment, we know charge is conserved, and we can see it move. It says we transfer it from the balloon to the fur, right? And then it's transferred from the balloon to the air. And the air is still within the classroom, and so this is still a closed system, and things are just moving around. All right. Consider the following 4 possibilities of point charges and see which one does not make a change. On this one, the best idea is just to do it out. Depending upon how your answers sorted, the first answer was the right one, but they were random on all of these. So let's just look at the first one. So we have K times 3Q1, right, times Q2. It says, oh, sorry, triple each. Triple each, and then triple the separation. So that gives us 3R, but remember it's that quantity squared. So this is 9KQ1Q2 over 9R squared, so that does not change it. Let's look at the next one. Triple 1 and triple the separation. So K3Q1 Q2 over 3R squared gives you 3KQ1Q2 over 9R squared. Well, that doesn't work. This gives us 1/3 of our original 4. Then it says triple each and reduce the separation by 1/3. So K3Q1 3Q2 over 1/3 R squared. Remember, put that in brackets. So that gives me 9KQ1Q2 over 1/9 R squared. Well, remember that fraction in the denominator is going to flip up, so this gives us 81 times our original force. And then the last one, reduce each charge by 1/3, so 1/3 Q1, 1/3 Q2, and then triple the separation. 3r squared. Well, this gives us 1/9 kq1q2 over 9r squared. And so the 9 here drops down, so it becomes 1/81st of my original. Notice that if I had done a third in the denominator, if instead of it had been triple, if it had been 1/3, that this actually would have been the same answer. This also would have been correct. You're going to have to be really careful about that on the test, and I suggest that you work it out step by step and make sure that it's making sense. Okay, an insulating object like a latex balloon and glass rods are charged by friction, and this was just what I talked about before. Insulators, the valence electrons are bound tightly. Conductors, there's a sea of free electrons. So if you pick this second one here, this is really talking about the conductor, and you need to read the questions very carefully because the question asks, why is an insulator? However, the insulators, do not make good electrical conductors because. So they're looking for you to explain why the insulator is not a good conductor, not why the conductor is a good conductor. Okay. So here we go. 3-point charges are given, and they say, what is the force on charge A? Well, we just draw a free body diagram for A. A is positive, so the force of B on A, B is opposite charge, so it's going to be an attractive force, so that's the force of B on A. C is also a negative charge, and it's also going to be an attractive charge, but it's also double the distance, so remember that if something's double the distance, then I get 1/4 the original force. So when you draw your free body diagrams, you should make sure that they're relatively sized, and you should be prepared to do that on the unit assessment with reasonable accuracy. So here it is. I add them together, and my net force is going to be to the right. Recall that the object will accelerate in the direction of the net force, so this is the correct statement here. All right. So on the next one they said, what is the force on B? Okay, well let's take a look at that again. So here's my 3-point charges, and here's my B. Okay, well, let's draw a free body diagram. So B and C are the same charge, so it's going to be to the left. They're going to repel. So this is the force of C on B. A and B are the same charge, and it's going to be an attractive, so here's the force of A on B. Notice that the vectors are the same size. They say it's the same magnitude of charge. They're equidistant from it, so they'll actually be the same size. Whoopsie. So you have this larger vector, and that's the net force on it, and it is indeed to the left, so it will accelerate to the left if it was free to move. All right, complete the following statement. Glass rod is charged with a silk cloth. I gave you the triboelectric series. These up on the top tend to lose electrons and become positively charged. These on the bottom tend to gain electrons and become negatively charged, and you should be able to use a triboelectric series for the unit test. Remember, it doesn't have to be all the way down on the bottom. It's anything underneath it. So if glass is rubbed with human hair, it's going to lose electrons to that human hair. So please be aware of that when you're reading this. So glass and silk, the glass rod is going to be positive. The silk is going to gain the electrons from the rod. Conducting sphere contains initially 2 microcoulombs of charge. A neutrally charged object is placed in contact with the metal sphere. And so what you see is a decrease in the amount of, in the shortage of electrons. So the neutral sphere is giving some electrons off, and that's why it says how many electrons are removed from that sphere. And this is just a quantization of charge. So you know that the magnitude of charge on the sphere when it's done is 1 × 10⁻⁶. You know the amount of charge for one electron is 1.6 times 10 to the negative 19th, so you just plug it into the formula very carefully, and you get 6.25 times 10 to the 12th electrons. A lot of electrons in 1 coulomb of charge. Please do not think that 1 electron is 1 coulomb of charge. And it makes sense, because if we talked about charging an object, charging the desk, or charging you, and we talked about 1 coulomb being equal to an electron, we'd be dealing with millions of coulombs, and that's just an impractical measure. All right. At what separation will 2 charges, each with a magnitude of 6 microcoulombs, exert a 1.4 Newton force on each other? Okay, so this is an application of Coulomb's law. Always good to draw a little diagram, and I have it here, and then I just rearranged the formula to find R so that I don't have to forget about doing the most common thing, and that's taking the square root here. Also, some algebraic mistakes can come up if you're not careful. So here it is, and 0.48 meters is the correct answer. All right, a 4 microcoulomb charge is located 0.3 meters to the left of a 6 microcoulomb charge. And so when I see that, the first thing I do is draw my situation. You have the negative charge on the left, the positive charge on the right. It says, what's the magnitude and direction of the electrostatic force on the positive charge? And so this is just another example of Coulomb's law. We could, now ask you to find the field, and recall that the electric field would be KQ source over R squared. So we could have asked you, what is the field produced by the negative charge, or what is the force produced by the positive charge, and you would have used this. Or we could have asked you what the field was, and you could have just on a given charge, and you would have said it's F over Q test. So don't forget, that's the next step on this unit assessment, is being able to work with the fields. Or we could have given you a spot in some, here or here or here, and you could have found the net field or the net force at that spot. All right, in a vacuum, 2 particles have charges, Q1, Q2, separated by a given distance. One particle feels an attractive force. Well, the first thing you should do is draw your diagram. If this is positive, right, this is positive, then the other one's got to be negative if there's an attractive force, okay? So that tells you right there, and drawing your diagram helps you remember when you're going back to your answers. This is another example of Coulomb's law applied. You should be able to do that formula for any variable in it, and we just plug through our work. I've marked which one you forget to use the squared on. This one with the positive, I think you just didn't do the charges right, but you should take a look at that again. All right, if a north pole of a magnet is brought near a south pole of another magnet, how will the two, opposite magnetic poles attract? Like magnetic poles repel, it's the same type of thing as opposite electrical charges attract and like electrical charges repel. So that's a similarity between the two. And you should expect on the test to be able to compare and contrast electric and magnetic fields. The north end of the bar magnet is attached to the end of an iron nail as shown. Which of the following is not an accurate statement, okay? And again, underlining things as you go through is really important. So when I attach that magnet to the ferromagnetic material, which is the iron nail, the domains will align. So this end of the nail actually becomes like a little south end of a bar magnet, and this other end ends up as a north end. So this end will end up doing everything that the north end of the compass needle will, as long as the magnet's attached. If I leave it attached for a very short period of time, the effects of this alignment will kind of go away. If I leave it attached for a few minutes, we might get the nail to hold the magnetic effect. The domains may stay aligned a little bit, but remember we said there are 2 ways to damage a magnetic field. One is heating. Recall the Curie temperature was the temperature at which the domains will start to randomize again. Or we can drop it, bang it, hammer it, And so this is wrong, the one that says that it'll become a permanent magnet regardless of how little time and what we do to it. That's not a true statement. All right, the image to the right is of two bar magnets. One is labeled, the other is not. What's the missing one? Well, look at this and you can see that the field lines repel each other, right? And remember there's this area right in the center where I have no net magnetic field. I could put something in the center of that field and it would have the magnets would have no effect on it. There's no field there. Or at least from these magnets. And so it would have south. These are likes repel, they're south things. And you should be able to do lots of things with that. Okay, that's it. If you have questions, send me